Thank you very much, Pavel Kroupa. I have to go it. He did his PhD at Trinity College in Cambridge in '92 as a Isaac Newton and Samuel Rousfall scholar, with the subject of the distribution of low mass stars in the Milky Way. And until 2000, he worked in astronomical research groups in Heidelberg and the Max Planck Institute for Astronomy. He earned his habilitation at the University of Kiel and was awarded the Heisenberg Fellowship in 2002. 2004, he was appointed to the Observatory of the University of Bonn and honored in 2007 with a Swinburne University visiting professorship in Melbourne and by a Leverhulme Trust visiting professorship at the University of Sheffield. He's now a professor and leads the research group on stellar populations and stellar dynamics at the University of Bonn. And since 2010, he has concerned himself increasingly with cosmology. 2017, he was appointed as professor hospitem at the Charles University in Prague. 2019, he was awarded the Crystal Rose by the town of Jindřichův, sorry for that, for his contributions in science. So apart from his papers, you could also have a look at his blog. He has a very nice blog. And he's here today to talk about the existence, or I would say the non-existence of dark matter. So please go ahead. Thank you.
Thank you. Thank you for the invitation, and pleasure to see you all here. I've never been to DESY in Zeuthen, so it's a really nice experience. And why did I drift into this dark matter cosmology problem around 2010? The reason is I was mostly concerned with stellar populations, and I was very happy with that, looking at star formation and how do we describe how the properties of stars have and how do they arrange themselves in binaries and all that. And then I started realizing that what we see in the data is not what the next door cosmologist is telling me what I should be seeing, right? And so I started investigating that more and more. And so here we are, considering the existence of dark matter, and I want to explain to you that it doesn't exist. Now, of course, that statement, as coming from, especially from an astronomer, can be suicidal in the sociological environment we live in, and I have good reasons to make that statement. Obviously, as a scientist, I would make a statement like that based on belief. So, what is the evidence? And that's what I want to cover today. So, first of all, we have to know the galaxy, right? Because the issue of dark matter comes up because of the properties of dark matter, because of the properties of galaxies, and not because of certain properties of stars. So the cosmological model defines the allowed population of galaxies, right? Now, the current cosmological model, of course, completely depends on the existence of dark matter, and so the properties of galaxies are completely linked with the existence of dark matter in the theory. And so one first question one can ask is what type of galaxy dominates the population? So you look at the sky and you count your galaxies, and then there are basically two types of galaxies. They are the elliptical galaxies and the disk galaxies. And which one dominates? Do you have any idea? I mean, I know you're a particle physicist, you might not really have been looking at the sky as such, but do you have any sense of what type of galaxy do you think might be more out there? Roundish, elliptical type galaxies or flat disk galaxies? Any idea? But feel free to, it's really not a problem to.
Elliptical.
So this is elliptical, looking elliptical.
Oh, we have this side of the table.
That's disks. Do you agree with ellipticals on this side?
So
okay, well, that's good because it's good to hear both sides. Now, I do this test many times, and many institutes I come and visit. I ask the young people; those are now actually astronomers and mostly observational astronomers, what type of galaxy dominates. And one might not believe it, but most of the young postdocs and PhD students do think that it's elliptical galaxies which dominate. And I do that purposefully because, as you will now see, there is something grievously wrong in the community. And so we have here an elliptical galaxy on the left, up here. You can see here about the scale. So this is about 15,000 parsecs, which corresponds to, oops, sorry, it's 3 times. So this is a wrong number. It's more like 50 or so thousand light years, just to get an idea. So that tells you how long it takes from one side of the galaxy to travel of light to travel to the other side. But the dynamical time typically is something like a few 100 million years. So the light travel time across a galaxy is insignificant compared to the dynamical times, which means we can treat the whole problem as being non-relativistic. So that's an important thing. And here are then 2 disk galaxies. So these are how disk galaxies look like. That's how the elliptical looks like. And a question we can ask in terms of this sort of picture: are these 2 galaxies merging? What do you think? Now, of course, you're, again, particle physicist, so you might not know. And alone me asking this question already implies that there's some hidden agenda there, obviously. So the typical astronomer would say they are merging.
Doesn't really look like it.
Sorry?
Doesn't really look like it.
You're a physicist, I know, but astronomers say they are merging. And that's exactly what's in the heads of these people. They are trained neuronal network, has been trained to recognize this automatically as a merging galaxy. But if you'd see 2 stars like that, you would never think they would be merging. Right? You'd think they're probably binary, just orbiting about each other, or they're just passing each other. Yeah? But the astronomer today is conditioned to say these are merging galaxies. So we'll come back to that a bit later. Now, and the two are related, because you can imagine you can take 2 disk galaxies, you merge them, you might get something which looks round, right? So 2 cars, you merge them, that looks roundish afterwards, right? Right? This is sort of basic physical concept here. So what dominates the galaxy population, ellipticals or disk galaxies? That's sort of related to this. Do galaxies crash and make ellipticals? How often does that happen? That, of course, depends on the theory we have. So since the 1980s, up here, it actually is known that disk galaxies are the most abundant galaxy type, which is why I'm very interested to realize that the modern day astronomer actually thinks that the ellipticals are dominant, which is strange, because which means something's going wrong in the education of the astronomers. If they go out of the master's courses and they have in their heads that galaxies merge and ellipticals dominate the population. And this then propagates through to all other fields. And you even read research papers where they sort of point out that ellipticals are an important population of the galaxies. Okay, so this is the distribution functions. So this here is the number of galaxies versus the luminosity on the x-axis, which is the mass. So our Milky Way is somewhere in this regime here. Our galaxy, these are more like dwarfish galaxies on this end. But we see, so this is the total number of galaxies as a function of luminosity. Here, very bright galaxies. You can see that these are the elliptical galaxies. This long dashed line here, that's the key up here. That's the ellipticals. And you see that the ellipticals are completely unimportant. They are a few percent of the whole population across the whole mass range. Only at the very massive end, and these are, you can see they are very rare, do ellipticals dominate the numbers. Disk galaxies, which are these short dashed line and this one here as zeros, are also disk galaxies, but both of them you can see. So the short dashed line is completely the dominant population. And the S zeros here are more dominant than the ellipticals over much of the regime. And then these dwarf galaxies here, again, the dwarf ellipticals, which is this line here, is not important. Yeah, the dwarf irregular galaxy, this dashed dotted line, is much more important. In fact, if you add this dwarf irregular and this galaxy, you get basically a flat distribution here. The dwarf irregular is a disk galaxy, it's just very small and looks less organized, because when a massive star forms somewhere, it might even outshine the whole galaxy. And so it looks much more irregular, but actually those are little rotating disk galaxies. And in galaxy clusters, exactly the same holds. And disk galaxies completely dominate the numbers. You can see here, these are the disk galaxies. But we now do have a larger fraction of ellipticals, but they are still rare. And it's only at you see that in galaxy clusters, we now have many more massive, very massive ellipticals at this very bright ends, but they are still very rare. And if we now look at the environment in galaxy clusters, even there, disk galaxies are completely the dominant population. Look at a galaxy cluster with 1,000 of galaxies, and it's the disk galaxy which you will find there. Ellipticals are concentrated towards the center. So this here is the fraction. You can see these are disk galaxies, and this is a function of this distance from the center of the galaxy cluster out to the outer regions of galaxy clusters. So this is a sum over many galaxy clusters. These are data from the 1980s, right? And the ellipticals you can see here are only a little bit more dominant at the center, but still significantly subdominant compared to the sum of the disk and S0 galaxies, which make up in this sum to 80% of the population, and the ellipticals are like 20%. In the really dense regions of elliptical of galaxy clusters, and here we have the same data now as a function of density, and you can see only at the very dense central regions of major galaxy clusters do we have elliptical galaxies, which now make about not even 50% of the population. So a galaxy cluster which is rich typically has ellipticals at the center, but there are still more disk galaxies there than ellipticals. Okay, so that's what we know from the 1980s. So elliptical galaxy population significant only at the centers of the densest clusters, and this does indicate, this is a strong hint that galaxy-galaxy collisions might form from them, might form from this galaxy. So this galaxy collisions might lead to the formation of elliptical galaxies. Now, a modern survey, this is now 2010 by the group in Paris around François Hammer, looked at the nearby universe. And I'm not even sure if they cite the older work from the 1980s in their paper, but you see that they find that in the nearby universe, ellipticals make up just 3% of the population. And all of these are rotationally supported disk galaxies, with a few being peculiar. There are probably galaxies which are encountering, so they're currently interacting, so they're distorted. But more than 90% of galaxies are disk galaxies. And 6 billion years ago, this is when the universe was half its age, we have here, according to their numbers, 4% ellipticals, and the rest are rotationally supported galaxies. On the peculiar fraction down here is bigger because the universe was denser, there were more galaxy encounters, and so they look distorted. These data clearly show us that the elliptical population does not increase with time, which it should have if the galaxies were crashing into each other and merging. And so this is an issue which already tells us there might be problems. So which galaxy type dominates? No. And the rotationally supported thin disk galaxies dominate by far the galaxy counts. So to understand a galaxy, you need to understand your disk galaxy, and the ellipticals are maybe for future studies. Of course, they are still very interesting objects. We don't want to disregard them. So the fraction of elliptical galaxies is insignificant and really constant, or even decreases a little. But that's probably just Poisson uncertainty, half the lifetime of the universe. So any theory of gravitation cosmology must be consistent with this elementary observation. And so the question then one can ask oneself, how come do the young astronomers today have a completely perverted picture of the universe in which the ellipticals appear to dominate? Like not everybody, but really a large fraction of young astronomers. How is that possible? I mean, I'm still trying to find an answer to that. I'm giving lectures myself, and I ask at each class, beginning of the semester, to the students, so what do you think dominates? And quite often they do think that it's the elliptical galaxies which dominate the skies. I mean, yeah.
So can they, I mean, this elliptical galaxy, can they convert into a disk, and can they evolve into a disk over time?
No. Only way to there's more subtlety to this. So we can actually look at the properties of ellipticals, and we know from the stars in these ellipticals that they formed just after the Big Bang very quickly, and the more massive they are, the more quicker they formed. The disk galaxies have stars which started forming 12 billion years ago, and the galaxies are still forming stars today, like our Milky Way, right? So if you take two disk galaxies and you want to make an elliptical, you can do that dynamically, but you would get a very wrong distribution of stellar ages in these final product. It is not possible to make elliptical galaxies from disks, and you cannot make a disk from an elliptical because, well, you can grow a disk around it, but like our Milky Way sort of, you could say, has an elliptical at the center and a disk around it. So this is possible, but that's the theory has to explain for the fact that you have the majority of these galaxies being disks, with some of them having bulges which look like ellipticals, but that's not the dominant fraction. They're galaxies without any central bulge at all, right? So they're just pure disk galaxies. So,
but are their brightness comparable? The brightness from the elliptical galaxy population, brightness from a big fraction of the disk one?
so again,
Is the brightness, are the brightness comparable?
of course, astronomers would hopefully account for the well, Malthus bias, basically. So the fact that you see bright objects to a larger distance, that is, so one takes volume limited samples. So, for example, if you take the nearby local cosmological volume of 11 megaparsec distance, where we really know nearly every galaxy individually, it's completely dominated by disk galaxies. Ellipticals you really have to go beyond the 11 megaparsec volume to get a few more ellipticals. Our local region definitely has very few ellipticals in it. So, yeah, it's not an issue of brightness, but the brightest galaxies are ellipticals, yes. That's definitely true.
But doesn't that introduce an observational bias?
Towards, yes, so certainly, but the observation astronomer should be aware of that, right? So you need to, if you want to understand your galaxy population, you can't just look at the brightest objects. So, so the theory must allow thin disk galaxies to remain thin disks galaxies over the age of the universe. Okay, so our Milky Way has a disk which is 10 billion years old and is very thin, which means over 10 billion years it must be made, right? It couldn't have been perturbed. And this is nearly true for nearly every other galaxy you might look at. So, those are sort of preliminary comments which tune you into the sort of issue which I was hitting already many years ago in terms of what they tell me I should be seeing, because that's what they see in the computer, or the cosmological community, versus what I see on the sky. And so let's now look at the cosmological model, the standard one today, the modern standard cosmological model. And that is based on two fundamental assumptions. The first of all, Einsteinian, Newtonian formulation of gravitation is valid everywhere, right? I mean, we would agree that's a very good assumption. The other one is that all matter is created initially at the hot Big Bang. What's usually not stated, it is, however, a very strong assumption. So, because this gives us the boundary conditions, you either calculate with all the matter there in the beginning or not, right? And this is currently the standard assumption. So with these assumptions, so these are the fundamental assumptions, and then we look at observations, and observations of, for example, the cosmic microwave background, which is basically completely uniform with tiny little fluctuations in temperature, and, for example, galaxy rotation curves. So both of these tell us that we need to introduce inflation because of the properties of the CMB. We need to introduce dark matter because of the properties of galaxy rotation curves, because we don't see the Keplerian decline. So there must be more matter. Assuming this, there must be more matter allowing the stars to go in circles around the galaxy at the speeds we observe. And again, comparing with this and the current rate of expansion of the universe in terms of supernova 1A standard candles, we must introduce dark energy. So, but you can see how this goes. These are the fundamental, very physically sensible assumptions. If you make predictions based on these, you do not get this and you do not get that. It's a total failure. This model is completely ruled out by the data, like massively ruled out. So to save this, we have to introduce these three new physical phenomena which are not testable in any other way. I mean, you cannot go and test inflation in any other way except say it happened. And you cannot do that with dark energy. You cannot go and test dark energy in any other way except to say it's there. And then dark matter, well, there we would have hope to see it in some experiments. If the cross-section for it to interact with normal matter is not completely zero, there might be a hope of finding evidence for dark matter in some experiments. So that's a hope. So if we could confirm dark matter, then we would have more confidence in this whole model, right? So no dark matter could be cold, warm, fuzzy, or axion. It doesn't matter at all because one has to explain rotation curves down to the smallest galaxies, and whether you now look at your dark matter particles being fuzzy or warm, it really doesn't matter in this type of discussion because it has to account for galaxy rotation curves. So you can't make it as fuzzy, i.e. the Broglie wavelength can't be much bigger than the size of the smallest galaxy, because other than this dwarf galaxy would not be full of dark matter. Right? So this constrains fuzzy dark matter. There's a hype about fuzzy dark matter now to have properties which basically are very similar to cold dark matter. Okay, so that's the one thing. And so we have this picture in our heads of the universe and in the computer. That is, there's the Big Bang, inflationary epoch. That's when the matter is created. Then we have the CMB, when the photons decouple from the matter, so we see the photons from that time still propagating to us, and then the universe expands and starts forming structures, and then dark energy rips it apart again. So it starts to rip the universe apart again, and today we observe the universe with our instruments, and hopefully this model would account for the properties of galaxies. Yeah, but you've already seen that there are some key features which the model must account for. So in the standard model of cosmology, galaxies grow mostly through mergers, and that already starts being a problem. That's why the young astronomer today thinks when they see two disk galaxies close by, they think they merge, because in the model, galaxies must merge, and I'll come to that later. So this is a sort of a merger tree from a particular calculation published in Stewart et al. 2008. So this is the redshift. So time, we go to our present time here. We are here down there at a redshift of 0. And this little one here is a dark matter halo which formed sometime probably from the mergers of other little dark matter halos after the Big Bang. And since dark matter doesn't interact with normal matter, it can just gravitationally collapse, make the first potential wells in which the gas falls in and makes stars. But you need the dark matter to seed the formation of structures, and that's what happens. So one starts off with a huge number of little dark matter halos which acquire gas, form stars, either become little dwarf galaxies, and then they merge. You can see this one here is now approaching the major dark matter halo, which is this one here, which itself is growing with time as it's merging with all the other galaxies until we see it today at a redshift of 0 to be the galaxy which we would be seeing on the sky. So this year, in this model, we have a redshift time relation. So this is the redshift, unfortunately it's covered now, but here we have the redshift versus time. So this curve tells us if I see a galaxy at a given redshift, I know at which time it is, but it's only valid in this model. If I have another cosmological model, that redshift, which is an observed quantity, would correspond to a different time. So that's really important to keep track of, because the ages of the galaxies we see at a given redshift might not be correct if this model is not correct. Okay, and so we see here, first of all, that in the standard cosmology, galaxies grow mostly through mergers. The question is why? Why do they merge? So two stars flying past each other don't merge, but two galaxies flying past each other merge, right? So why? And why are most galaxies ancient in this galaxy? Okay, so you can see already a problem. Imagine our Milky Way has this history of mergers, and every galaxy must have a history of mergers, because you cannot make a big galaxy without all these mergers. How do we manage to keep it having an ancient thin disk over all these mergers? I mean, if you look at Formula One racing cars, and you go around and you imagine that each car crashes a few times, it would not look like a Formula One racing car afterwards. Here the galaxies appear to still keep their thin disk structures despite all this merging. And so this is already, you can see some tension with the actual data. So if you remember this slide, I had this slide, any theory of gravitation cosmology must be consistent with this elementary observation that the fraction of ellipticals is insignificant. So it must allow thin disk galaxies to remain thin disk galaxies over the age of the universe. That is basically already telling us that the whole model doesn't work. And this is realized since 2008. I mean, the paper I mentioned to Stewart et al. Has exactly that statement. It says that it becomes a problem. How do we explain the thin disk galaxies if there's all this merging going on? Nevertheless, the community continues on this model. And so let's look at galaxy rotation curves. According to the standard model of galaxies, standard model of cosmology, galaxies look as follows. So we have here our Milky Way, for example, and this is the dark matter halo. You can see up here the scale. This is 250 kiloparsec. You multiply that by about 3 to get it in light years. So it's nearly 700 or so 1,000 light years. And what are all these clumps? All of these are dark matter clumps which are orbiting around this Milky Way. There are thousands of such satellites around our Milky Way in this theory, and many of them should have little galaxies in them. And that's a consequence of this merger tree, because all these little dark matter halos, they merge, but on the scale here, that many of them keep orbiting within the galaxy. This point is this whole thing here. So all of these here are actually the remnants of this merger process, which grew the whole dark matter halo and the galaxy to the current size. So that's what it should look like. This leads us to a fundamental problem. If you look now at the inner part of the galaxy where we have the visible matter, that we cannot predict the rotation curves. So we are accustomed in macroscopic physics to be able to predict the properties of macroscopic objects, right? We are accustomed that in quantum field we can't make clear predictions because there are probability issues and wave functions and so on, expectation values. But in macroscopic objects, we would have so far always thought that we can predict if we know the theory well, we predict exactly what we should expect once we construct something. And so here we now have the first, to my knowledge, macroscopic theory in which we can make no prediction about how fast the rotation curve is. So the astronomer maps out the mass distribution of stars and gas, which we can do with radio telescopes and other telescopes. And from this observation, it is not possible to calculate how fast the matter is going around the galaxy.
So, Pavel, is there a way to calculate the average angular momentum of, a region like the one you've shown before in these simulations?
Well, one can do it in simulations, of course.
Yeah, right.
Yeah.
But I mean, then how much is it compared to what you, in the end, need to form a rotating structure? Because that has a non-zero angular momentum.
Yeah. I'll come to that in a moment. So the point now is that from such data, we cannot predict how fast the galaxy is rotating. We cannot predict its angular momentum just from the observed matter, right? So here's the example. Why can we not make a prediction? And the reason is because we do not know the potential. And so from this work, we have here the mass of the galaxy. For example, our Milky Way has 10 to the 11 solar masses in stars. And this is within a dark matter halo, which makes most of the potential. And that dark matter halo is given, it can be either that mass or that mass, as you can read off on the scale. So you can see that our Milky Way would be in a dark matter halo, which can have a mass of 10 to the 12 solar masses here, or a mass of 10 to the 13 solar masses. So that's the dark matter halo around the galaxy. And the thing is, we don't know what dark matter halo our Milky Way has. which means we cannot actually predict the rotation curves because we have a factor of 10 difference in the dark matter halo it could have, right? So that's the one problem. So in the calculation, yes, in the computer, each of these points here is a galaxy which forms in the simulation, and that has a clear-cut angular momentum and everything. But that's in the computer. Now, if you look at the observed galaxy, how do you match the observed galaxy to any one of these points? That's the problem, right? Because we cannot observe the dark matter halo. Furthermore, the concentration of the dark matter halo differs. So here we have again so this is now the log C, which is just the concentration. So our Milky Way can have this mass in the dark matter halo. It can have a concentration down here, which is a small concentration, or it can have a concentration which is even up there, which is a high concentration. And you can see that the dispersion is more than an order of magnitude, which means you can have our Milky Way in a dark matter halo which has some sort of mass, and it has a compact inner potential or not a compact inner potential, but you don't know because it's not something you can observe. You can only observe the normal matter. And so here is the visualization. We have our Milky Way, and it now has this dark matter halo. The dark matter halo itself could be rotating this way or that way. We don't know. It could have, then you would say if it's this particular dark matter, you would predict this rotation curve. But then the dark matter halo could be squashed somewhat. It's not exactly spherical. Then you would predict for this galaxy this rotation curve. So this is the speed of stars going around the center of the galaxy as a function of the distance of the galaxy, right? So in this particular case, our sun is at 8 kiloparsecs approximately from the center. And in this particular example, the rotation curve will be dropping as we go out away from the center. Or if the dark matter halo is this particular shape, the rotation curve could be looking like that. Yeah, so rising. The point is we simply don't know. There's no way to predict the rotation curve from the observed galaxy.
What about the neighboring galaxies within a cluster?
The same problem applies.
Is there any correlation on the density?
Well, there are weak correlations. You could see that there was a scatter plot, and there's a correlation, right, in terms of the properties of the dark matter halos. But the scatter is of order of magnitudes either way. So, and then in galaxy clusters, it gets worse because the galaxies are moving through the cluster of the dark matter halos being lost partially, and so that in addition changes the properties of the dark matter halos. So. So we cannot predict rotation curves from a measured mass distribution. So that's the problem. And here now are some examples of measured rotation curves. This is a galaxy, which you can see rotates with a speed of 300 kilometers per second. And the rotation speed, you can see how incredibly regular it is, basically completely flat out to 60 kiloparsecs in this case. Our sun in our Milky Way is at about 8 kiloparsecs. It's about the distance, and our Milky Way rotates only at about 250 or 220 kilometers per second. So this is a giant, massive disk galaxy. But you can see how incredibly flat the rotation curve is. And here's an even more massive galaxy rotating at nearly 400 kilometers per second. You can see how incredibly flat the rotation curve is, out to 80 kiloparsecs. And then we have some dwarf galaxies which show very nice regular rotation speeds. Here, this is only 15 kilometers per second. This galaxy here has a mass which is that of a globular star cluster. It's a little rotating disk galaxy. It has its gas in it. It's making stars. It's a beautiful rotation curve, and it has a mass of a massive globular cluster. And then we have this galaxy here again with a nice rotation. Now there are clear-cut correlations in the observation of the slope here versus the mass of the observed galaxy and this speed which at the end points, which there have been tests, and it's not easy, it's not really possible to explain these type of correlations if they are dark matter halos. But the question we can now ask directly is, do we have evidence what creates the potential in the galaxy? Is it the dark matter? Or not. Now, the thing is, what I've been saying so far has not removed dark matter from the table. It's just telling us that dark matter has properties which we might find difficult to work with.
But here we now start seeing evidence against dark matter. In this particular case, we have here a rotation curve of a galaxy. You can see it has this type of dip. And this is the rotation curve we get from the gas in the galaxy, and the stars are not visible here, but they go somewhere down here. So this is a dwarf galaxy, which you can see because it's rotating with a fairly slow speed, only about 80 kilometers per second. Most of its mass is in gas. Maybe 110 or so percent of it is in gas. And the rotation, so the gas and stars together cannot create the speed. You need the dark matter to boost up the rotation speed to keep the galaxy together. And if we now take a galaxy from these simulations, which would best fit this rotation curve, it would have a dark matter halo which looks like that. So that's the inferred dark matter halo in order to match the observed gas and stars to the observed rotation speed. The problem is that the dark matter halo is smooth. Because the dark matter particles are moving around fast, and it's a pressure-supported system, it's spheroidal, while this galaxy is a thin disk, it's rotating, and so the rotation curve, which is made by the whole potential, stars, gas, and halo, is this solid curve. It has a little bit of a dip because, yes, the gas and stars do contribute to the potential, but most of the potential is made by the dark matter halo, and it is not possible in the dark matter framework to explain these type of dips. These dips come about because here we have a galaxy. You see here we have a density wave, which is a denser region in the galaxy. Here we have an interarm region, which is a less dense region, and so the matter, as it rotates around the galaxy, it speeds up as it falls into the potential of this spiral arm. And then as it comes out, it slows down and then speeds up again as it falls into this spiral arm. And so we see these variations in the rotation of the matter. But that cannot be the case if the potential is dominated by the dark matter, because then the rotation speed is basically uniform, and these density waves don't really affect the.
That's a very naive question. So here you have like one-dimensional distribution as a function of distance. So my very stupid question: whether the velocity changes like a function of angle, or it's like a really constant.
Yes. So what we do is we can only in these cases observe the line of sight velocities from spectroscopy, radio telescopes, or stellar light, and so this is a face-on galaxy. So this is here we cannot really get a good rotation group in this particular case, but there are galaxies which are inclined, which look like this, just that they're inclined, and there we can really map out the velocity field very nicely along the line of sight. The third and the other two dimensions are then not really known, but since it's a thin disk galaxy, you don't have so much options. I mean, the stars cannot be going out of the disk, because otherwise you would have the disk. So the matter must be confined in rotation to the disk, and the line of sight velocity then tells us basically most of the rotation. But there are some uncertainties in this in terms of the second dimension, but the rotation speed here is something like 200 to 300 kilometers per second. And the rotation, the speeds of the stars out of the disk in such a galaxy would not be more than something like 30 or 40 kilometers per second, which means the perturbations through non-planar motions are not more than some 10%, which is not enough to make these particular wiggles. Yeah. And so this here, it cannot be explained. So this is Renzo's rule, the fact that you see the wiggles in the rotation curve are created by the wiggles in the observed mass distribution. The stellar distribution also has such a wiggle here. And this is called the Renzo's rule. It's well known. So wiggles in rotation curve correspond to structure in the density of observed matter. And that obviously means that the baryons are sourcing the potential. It's the baryons, which means stars and gas, which creates the potential. And there's no trace of any other source because we do not see this evidence for this flat potential or the smooth potential.
Are these wiggles observed in many of these, in all the rotational curves.
Yeah, some have less pronounced wiggles, some have much stronger, more strongly pronounced wiggles. So this by itself already tells us this can't be the case. And here's just an example. I'm not going to talk much about more because time will not permit it. But this is just an example. The same galaxy now modeled only in the Milgronian framework. So you don't have dark matter, but the gravitational force law is modernized. And then you can see that we can, just given the observed mass distribution, here you can see the stars. We can reproduce the observed rotation curve very nicely because in this case, the stars and gas source the potential, the Milgronian potential, while here you need the stars, gas, and a dark matter halo to source the Newtonian potential. The Newtonian potential, as a consequence, is smooth, while here, of course, the Milgronian potential is not smooth because you only have the stars and gas sourcing potential, right?
So one more question, please. So the Milky Way, for example, has dwarf companions like the Magellanic Clouds, right? So, and if you look at their orbits, you might imagine that at some point they simply punch through the Milky Way disk. That creates, I mean, either you may still see them while they're there, or they may have created some kind of perturbation that you still see. So things are not in equilibrium. So surely someone looked into this, and
But that's the wavelength for this perturbation is tens of kiloparsecs. But the wiggles are on scales of kiloparsecs.
Okay.
So that counts.
So you can't have a sort of some kind of subhalo or so that
Well,
distorts things.
this would be a hope, but it doesn't. That doesn't help because these wiggles are not in one place, but they are actually like over a larger region of the galaxy.
Like a spiral arm or so.
Yeah.
Okay.
Yes. So strong indication against dark matter. Right? Now, there's no formal test of the theory given this, but it basically means that if you would do a chi-square test, you would be able to account for these. So, despite these problems, the existence of dark.
But can you maybe try to Steelman? I mean, what do the proponents of lambda CDM say about this?
Yeah, that's a good question. I'm not sure.
They just ignore it?
I think this type of problems are probably one would say it's some sort of subgrid physics problem. So, so the standard like statement I have in my head is that it's the stars and gas are complicated, and
Turns out they are.
computer simulations are not good enough yet because it's subgrid physics. You can't resolve that well, and so one needs more. One is to try to improve the resolution of the simulations to maybe address this problem.
So the idea is to create some non-uniformities in the density of the dark matter to correspond to this. So.
That can, I mean, yes, but that doesn't work. I think that's very obvious.
Because the simulations work with huge particles, huge masses, right?
Yeah, but it's again not so. I mean, these so the resolution is better than the few kiloparsecs, and you see these wiggles, and one cannot make these type of wiggles. I mean, you can set up a high resolution model of a galaxy with a dark matter halo, and this can't be reproduced. These type of wiggles. You'd have to create your dark matter halo in a very specific way to do that, right? But then. How does one create such a very specific dark matter halo from the theoretical point of view? That's really possible. If you look at as I was saying, that cosmological simulations and then catalog all the dark matter halos which form in the cosmological simulations using very different codes and subgrid physics prescriptions for the galaxy formation. And they do not have these properties to explain these wiggles. You can probably always find some exception. There was a galaxy which just had a merger, which has a strange velocity field. So that's why I'm saying that this is a problem, but I haven't said that this falsifies the dark matter. Right? It's an issue of tension. I would always refer to this as a point where one feels uncomfortable as a scientist, because you can't actually see how I can explain these wiggles. On the other hand, there are all these issues. Is the resolution high enough? Are there perhaps just some configurations which could create that in some particular case, and so I don't consider this to be a formal falsification of the theory. It's just like, well, I'm building up the point that there are all these tensions. The theory makes clear-cut predictions. The potential should basically be smooth. It's observed to be not smooth. The theory predicts galaxies should be merging like mad. What we see out there isn't really showing that. Okay, these are the sort of just pointing out this overall tension building up, right? So you see, that's why, despite these problems, the existence of dark matter particles is an originally well-motivated physical hypothesis. So because we are still based on the idea that we want to keep Einsteinian gravitation, Newtonian gravitation, for that then we need dark matter. Those are really important assumptions. Therefore, one would now not discard this theory just based on those type of tensions, at least not yet. Okay, so if we assume Einsteinian gravitation, then we need the dark matter. It's not possible to have a universe without dark matter if we keep Einsteinian. So the central pillar of the Stern model of cosmology is cold or warm dark matter particles must exist, otherwise the model collapses. If we can verify or falsify the existence of dark matter, the whole model is off the table. There's no point in discussing it. So one needs to find the dark matter, and yes, there's been a huge effort, an overwhelming number of dark matter searches since the 1980s. I don't know what all these mean, but you know, we can Google and find. But people are basically looking for dark matter under the ground, on the ground, and above the ground, wherever. You know, nothing has been found since full 40-year effort, as you all know. This doesn't mean it's not there, because the dark matter could have the property that it actually doesn't interact at all with normal matter. It's just gravitationally. But you can see that this is not a good scientific hypothesis, right? It's like saying, well, they are angels, it's just we can't see them. I mean, but it doesn't mean that it's not impossible, right? I mean, there could be angels, there could be dark matter. But there is a way to disprove dark matter, or I should say to test for the existence of dark matter. Of course, today I know it's disproven, but the formal scientific method is to say, which test can I think of which tests for the dark matter particles? And that's Chandrasekhar dynamical friction. So this is an elementary process which you find in any textbook on dynamics, gravitational dynamics. And Chandrasekhar formulated this, I don't know, 1940s or so. And it works like this. So just going back to our solar system, it's the Chandrasekhar dynamical friction is based on exactly what I'm showing you here. What you see here is the solar system. So the sun, the Earth is this blue circle, that's the Earth orbit. This here is Jupiter, Saturn, Uranus, and Neptune. And the question we have is we want to send a spacecraft to Pluto. So you don't build your huge rocket and power it up and shoot it out from the inner solar system, because that's an insane of energy you need, an insane amount of energy. What one does is one uses slingshot, right? So one first allows the spacecraft to fly past Mars. It gets accelerated, and Mars loses a little bit of velocity, so energy. And the spacecraft then goes out further to Jupiter. It does the same thing. Jupiter gives a little bit of its energy to the spacecraft. The spacecraft races out further, and that's how you sort of hop out of the solar system step by step by these slingshots. And that's completely well known. It's used, as you know. Oops, sorry, it's gone beyond. Yeah, so you can see the spacecraft as it's interacting with the planets, and it gets faster and faster and manages to climb out of the potential of the solar system. As a consequence of each of these encounters, each planet gets a tiny little bit slower. Okay, and so what now happens, if we have the situation with the galaxy, so we have here the galaxy which has its dark matter halo, and another galaxy with its dark matter halo enters this dark matter halo. That's what we see, this whole merging process. So what now happens is that, so this dark matter halo here is made of an incredible number of little small particles. And so we now imagine that we have this galaxy which is propagating through the dark matter halo of the other galaxy, and each of these is a little dark matter halo. It could dark matter particle, could be an axion, it could be some fuzzy dark matter or some WIMP. It doesn't matter. The point is that this galaxy moves through this background of dark matter particles, and each dark matter particle gets diverted through the gravitational action of this galaxy. So there's an exchange of momentum between the motion here and each little dark matter particle, as a consequence of which a wake builds up over behind this galaxy. This is a way of visualizing it. So this wake, which is now an overdensity of dark matter, pulls back at the galaxy and decelerates. And technically, what you do is you integrate all these encounters from all sides over all distances. That's what's stated up here. Integrate over all satellite dark matter encounters. And one gets this formula for the deceleration. So this galaxy moves through this background of dark matter particles, and it loses its kinetic energy, which is absorbed by the dark matter particles. So it's exactly the same as happens in the solar system. These dark matter particles are basically accelerated, and this one gets a little bit slower after each encounter. This is the formula for dynamical friction. So this galaxy loses velocity with this equation. And the important thing to note here is that the deceleration or dynamical friction depends on the mass density of the dark matter particles, not on the mass of each individual particle. It doesn't matter whether you have axions, some ultralight fuzzy dark matter particle, or a WIMP, or even little black holes. The density is what matters. And the density is given by the CMB conditions. You cannot change that number. You've got this number fixed by the theory. There's some variation because of the statistical variations, but actually this is fixed. And so this is well calculable. And we can calculate how quickly the galaxy should be losing kinetic energy as they move past other galaxies.
What's that X?
Sorry, this X is just ratio between the velocity of this galaxy divided by the typical velocity of the dark matter particles, which
again has to do with the potential.
Yeah. So exactly. So all of that is fixed. So exactly. So the X depends on the mass of the dark matter halo, which basically specifies the typical velocities, so the velocity dispersion of these dark matter particles. Therefore, we have this situation: the galaxy comes in, and then as it orbits, it loses energy and falls towards the center. If it gets slower, it falls into the potential. Right? That's the dark matter wake, and so we get the merger, and this is why galaxies merge, but only in the dark matter theory. If there is no dark matter, if this doesn't exist, it is just a different potential, then the galaxies don't merge. So you can already see the directions going, right? This theory absolutely requires galaxies to merge all the time, while we see a lot of these galaxies out there. The two don't really go together. And so we can now test for this effect through the orbits of satellite galaxies.
Yeah, about 10 minutes.
Yeah, okay, so I should be here. So I can tell you in a nutshell, I don't know if you see this whole thing, that to convince the community about this whole problem of dark matter takes time, and I never get to the point of actually going, saying dark matter doesn't exist, let's just forget about it. What do we do? Right? And now that's, of course, maybe more interesting part of this whole game. However, everybody is convinced there is dark matter, so we have to deal with this first. So this is a typical dwarf galaxy. So we have our Milky Way, it has these satellite galaxies, as you mentioned. And we can study the motion of this type of galaxy around the Milky Way. So we've looked at this a long time ago. In this paper in 2011, we looked at that time, we had the motion vectors of only 4 satellite galaxies, which means since we know the mass in stars, we can calculate the mass in dark matter the galaxy must have, according to the theory, and then go backwards in time. Now, going backwards in time means we accelerate the galaxy outwards, right? Because if it falls in, it's losing energy and spiraling into the galaxy. If we go backwards in time, we accelerate it out. So we do the calculations, and in this paper, we showed that for these galaxies, which must have been orbiting our Milky Way since 10 or 12 billion years, there is no inflow solution. You can't get it done because these dwarf galaxies are at the moment, they are too massive, too far from the Milky Way, too old, and too fast. You can't get all of this matching in the dark matter framework. So that's one test. So no significant dark matter halo around the Milky Way. If there's no dark matter halo, we are happy, they just orbit forever. And that's no problem. Just have to form them. We know how to form them in a non-dark matter theory. Now, there's another test which is related, compact groups of galaxies. It's more recent. So we have here this system. We have a local group of galaxies with our Milky Way and Andromeda and the satellite galaxies, and then something like 3 million parsecs away, or 9 million light years approximately, we have this group. It's basically the nearest group between us and them. There's not much, maybe a few dwarf galaxies, not much. Okay, this is the next sort of group which we can see. It has a Milky Way type main galaxy, something which looks maybe like well, a fairly massive disk galaxy here, and then this galaxy and this galaxy. These are little smaller disk galaxies, but what we see from this picture, the red is hydrogen gas observed with a radio telescope. And we know the motions of all these galaxies from spectroscopic analysis. We know that this gas is associated with all these galaxies. And to get this type of morphology, see, this is a huge tidal arm, and here's another tidal feature. To get this type of morphology, these galaxies must have been orbiting about each other a few times to spread out the gas into this direction. It's not possible to have them one encounter, another encounter, and then they merge. You can't get this type of morphology. So this has been looked at in 1999 by Korean Yoon. And he published a conference proceedings pointing out that there are no solutions with dark matter. He could not find any solutions. He had to take the dark matter out, then he gets solutions. In Newtonian gravity, it's still possible to find solutions. You wouldn't match the kinematics in the galaxy, but you can get solutions. With dark matter, nothing. And then he stopped. It's hot potato. He never published a refereed paper on this. You might think, okay, it's all completely wrong. But then an American team did exactly the same thing, remarkably at the same time, and they find no solution to dark matter. It's impossible. Again, the conference proceedings, then they drop the matter. It's a hot potato. You couldn't go around the landscape saying, I can't get it to work with dark matter, because at that time it was suicidal. It's still suicidal today, actually. And so we looked at this. Now, Wolfgang Oehm is not, well, he got his PhD at Bonn University. He left academia, so he became wealthy enough with his software capabilities to now be an independent scientist. So he teamed up with us. It's actually coming now as a visiting researcher, but he's not under sociological pressure, which means we could tackle this problem remarkably. And here's just a nice example from this calculation. This shows the force in whatever units doesn't matter as a function of the velocity of a galaxy of M81. This is one of the galaxies moving past M82 at the distance of 10 kiloparsecs. So the question is, so the galaxy is moving at 10 kiloparsecs around the other galaxy. The gravitational force, of course, is constant here. And the dark matter, the Chandrasekhar dynamical friction, the force which makes it go slower, is this curve here. One with respect to the other, and then the other one with respect to the other. So the one moving in the dark matter halo of the other one, and then the other one in the dark matter halo of the other one. So the point here is that the dynamical friction force becomes similar to the gravitational force, which means it's a very significant process in this group. And there's no way you can get out of that problem. You cannot solve this. You cannot suppress these curves down in this theory. And then these are the other galaxies. You can see that the dynamical friction is very significant compared to the actual gravitational acceleration. So we calculated the orbits. This snapshot using a genetic algorithm and a Monte Carlo approach to infer all possible initial conditions which lead to the current configuration given the line of sight velocities and the distances of the galaxies, but we don't know the line of sight distance, so we had to search all possible parameter space. And of all the solutions, these are the best ones. You can see here, we are today here. These are the distances of the 3 galaxies we looked at. So we get a current snapshot which looks like the system. Then it merges very quickly, which is okay. We don't know what's going to happen in the future. But in the past, these conditions are unphysical. They are unphysical in the sense they are not conform with the cosmological model, because essentially it means that the galaxies must have come, in this case, 7 billion years ago, from completely different regions of space. They would have been moving opposite to the Hubble flow, which is impossible, because the Hubble flow is observed. So we know that all the galaxies are moving away from each other. So they would have been opposite to the Hubble flow, and basically at the same time, magically, they meet each other, have one encounter, and then merge. Right? And we did this analytically and with an actual n-body code where the dark matter is live. So we have the full dynamical process, basically the same solution is obtained. And so Chandrasekhar dynamical friction shows that this does not work because it's basically arbitrary unlikely. You cannot get the galaxies in a part of the universe which are megaparsecs apart to actually move towards each other, because they at small peculiar velocities and they have to follow the Hubble flow, right? So this and now basically falsifies the existence of dark matter with basically infinite confidence, right? Yeah, and so I'll stop here. You've seen 2 tests being done. Okay, just one more slide. So there are many subgroups, which means it makes it even worse, because it's not just this one group, but you look at these compact groups of galaxies which are old. The galaxies seem to have been orbiting about each other for quite a long time. And so there's no significant dark matter at all. And so I think I will just end here then. You've seen a part of this. There's a 3rd test, which is very rigorous, based on the bar speeds of galaxies, which falsifies the dark matter existence with more than 5 sigma confidence. This has been published, and then there are, the thing is then at that point, the dark matter is formally falsified to exist. You cannot get it to work with dark matter. And for me, dark matter is off the table. It's not a relevant scientific theory anymore yet. Because of the sociology of the whole situation, the thing is that despite this falsification, everybody still is convinced the whole model works. So if I'm correct and dark matter doesn't exist, are there independent indications that the whole model doesn't work, right? It would be strange to say that, for example, your inflation model with dark matter and dark energy fails these tests rigorously, but then all the other tests like large-scale structure, how is matter arranged in space, are all consistent with the model. This would be a bit strange, right? So we've been looking at other tests, for example, the structure of the local group. How are galaxies arranged in the whole local group? And there we see that the local group looks more like a crystal. It is, for me, I call that a frightening symmetry, because we see that on megaparsec scales, the galaxies are arranged not like you'd expect some sort of gravitational object where the galaxies are orbiting about each other, but they seem to be stuck in megaparsec, million parsec large, 50 kiloparsec thick, so ultra thin, huge planar structures, which seem to be repeated again. And when we go away to more megaparsecs, we lose the line of sight distance information, right? Where we have good line of sight distance information, we see a frightening arrangement of matter on megaparsec scale, which currently no theory is able to actually account for. So that's just one issue. The other issue is that large scale structures, so now looking at hundreds of megaparsecs and gigaparsecs, we see that the lambda CDM model is a complete failure. We see huge bulk flows of matter of hundreds of maybe thousands of kilometers per second. So looks like thousands of galaxies are moving just one direction. And then if you look at construct your reference frame from the CMB, and you can measure the motions relative to the CMB, and we can construct an alternative reference frame using AGN and quasars, which should also be an initial reference frame. The two don't agree. It's more than 5 sigma confidence, which is not possible because they should be agreeing on those scales, right? So actually looking at the literature and all the research which has been published in the last 10 years, it seems that the lambda CDM model, so the model based on Einsteinian gravitation with inflation and dark matter, is a complete failure. It is not a functional model of the universe, right? And so with that conclusion, one now has to wonder which direction do we go. And of course, in Bonn and Prague, increasingly Nanjing and St. Andrews, we are now exploring completely different pathways. And I'll end with that. So thanks.